Hello, my name is Dylan Hacker, and today we will be discussing two spherical tanks at steady state with liquid inside of them and some flow rate going in and out. To start, I would like to draw the problem. We have tank number 1, some sort of intermediate stream, going to tank number 2, and this is in a series, and then we have some outlet stream. So starting off, we have an inlet stream into tank 1, which will be known as QN1. We have some inlet stream into tank 2. That's going to be known as QN2. We have this pipe right here, which will be known, the flow rate of this will be known as Q1 to 2. It also has some area, which is A12. Q2 is going to be the outlet stream. A2 will be known as the area for that outlet stream. And each of these tanks is going to be filled with a liquid. H1, H2, we'll say that's some liquid level. And our goal is to find the change in height over the change in time of these two tanks. So starting off, we have to figure out the flow rates. What are they equal to? Q12 is going to be equal to that area, which will be known, times the velocity. Now we don't know the velocity right off the bat, so we're going to have to find that. How do we find that? Bernoulli's principle. P2 minus P1 delta Z. P2 minus P1 plus delta Z times G plus the change in velocity squared minus V initial squared. And this V initial is going to be equal to 0 over 2, so we can discount that. That's going to be equal to 0 in this case because the change in heat will be 0. And I forgot to put this over rho, that is P2 minus P1 over rho. P2, in this case, is going to be equal to 0. So we have negative P1 over rho, which is really equal to negative rho GH. In our case, that H is going to be H1 minus H2. So once we have that right there, we plug everything in. Our delta Z is 0 because there is no change in height over that pipe stream. We get V12 is equal to the square root of 2G H1 minus H2. Now that can be an issue right there. So we have to put in absolute value of H1 minus H2 because in the case that H2 is higher than H1, that will be a negative, and a negative under a radical sign cannot happen. But we will make up for this later by adding a sign of this value in our equations later on. So once we have that, we know that Q12 is now equal to the area 12 times 2G, absolute value H1 minus H2. So we have that right there. Now we need to find what Q2 is going to be equal to. Same values apply, area times 2. And since there is no change in height values for the pressure, there's just one, it is just going to be H2. Now that we have that, we can use our mass balance and change in volume over change in time to find out the delta H over delta T, the change in height over the change in time. So at steady state, if it is at steady state, we know that Q12 is going to be equal to the Q in one stream, and the Q2 in stream is going to be equal to Q2 minus Q12. Now that will help us in just a moment when we're trying to find our dV dt. So those two equations are at steady state. So now finding the change in volume over the change in time of the first tank, we're going to get Q12, the inlet stream, minus A12, the area of A12, times, this is where the sign of that H1 minus H2 comes in handy. So that's either going to be a 1 or a -1 value, especially when we write our code here in just a moment. I will code it out with the specific values to test our knowledge. So we have that right there, and we don't want dV over dt. Remember, we want dH over dt. And that right there is equal to dV over dt over the cross-sectional area. This should not be, this is Q in 1. Don't know why I wrote Q2 there. So once we have that right there, we're going to dH1 over dt is going to be equal to Q in minus forgot to multiply by the square root of 2gh1 minus h2, that's the absolute value. And in just a moment, I will solve for the cross-sectional area of our spherical tank. But we'll leave that in a minute because we're going to have to solve for dV2 over dt, which is going to be equal to the inlet stream plus the other inlet stream. Remember that our Q12 is going to be an inlet stream for tank 2. We have to account for the sign again, H2 minus H1. H1 minus H2, absolute value of that. So once we have that, we're going to have to subtract it from our outlet stream. And now we have to solve for dH2. So just putting that whole equation right there over the cross-sectional area. So now that we have those two equations, we have to solve for the cross-sectional area. That is not the best circle. That'll have to do. So in our spherical tank, we have some height of HT. We have the water level at that height. going to change this to R. So to get the cross-sectional area, this water level right here, we'll call this R of T. This is little r. We have to use the Pythagorean theorem of this triangle right here. We know that this is R of T. We know that this side right here is going to be h of t, the height of that t minus r, because the radius coming down, minus r. And then this is r. So we get r squared equals rt squared plus h of t minus r squared. Once we have that value, we would want to solve for r of t. Oh, the parenthesis goes right there. And that value right there will give us r squared minus r minus h, or h, r minus h squared. We multiply this puppy by pi, and we have our cross-sectional area. We have to plug those back into the equations to get our final dh1 over dt. It's going to be equal to the q1 in minus a12 times the velocity. Don't forget the sign of h1 minus h2 to account for that in the square root. 2g h1 minus h2, absolute value of that, over r squared minus r minus h squared times pi. And then for dh2, same thing goes. q2 in minus, or plus in this case, h12 times the sign not sing, of h1 minus h2 times the square root of 2g, absolute value of h1 minus h2, minus the out flow rate, which is a2 square root 2gh over pi. This is h1, this is going to be h2, and the r's are also. There you have it. Those two equations we will be putting into our code, and I'll show you how to code here in just a moment. And I'm back. Alright, next we're going to be coding out the problem that we just solved for. We're going to be doing an initial value problem. We're going to do dh dt, and we're going to be making some graphs, some plotting, all through Python using Google Colab. And to start off, we have to get some libraries going for our code. And the first one is going to be solve IVP, which is going to be able to solve the initial value problem, dh over dt, for us. So from scipy.integrate, we're going to be importing solve underscore IVP, the initial value problem. We're also going to be importing NumPy, which stands for numerical Python, which will be able to do some of the functions, some of the math functions we need to be able to complete our code. So we're going to be importing jax.numpy, and we're going to be labeling this as JNP, so we don't have to be typing out jax.numpy every single time we want to use it. We're also going to be importing jax. This will mainly be for our switch variable, which I will talk about later. We're going to be using it for the sigmoid function, which will allow us to turn on and off or make it more realistic situation for our tanks. We're also going to be doing some plotting, like I said, so we're going to be needing to import some libraries from plotting. We're going to be importing from plotly.subplots, and from there we're going to be importing make_subplots. We're also going to be importing plotly graph objects, which will allow us to do more things with our graphs as we make them. And we're going to be labeling that as GO, and stands for graphical objects, also known as Go. Make sure we click run on that to make sure there's no typos in there, and it can import all of the appropriate libraries. And I did do it wrong. Okay, so what I did was I forgot the S on graph objects. And now it works perfectly. So you always want to be making sure that you run your code to make sure there are no typos throughout the whole code. So now that we have our libraries imported, we want to go ahead and start off with the initial variables, the radius, height, area of the pipes that we will be using, and then that will be able to lead us to our initial flow rates at steady state. So I'm going to start off with the radius of each tank. The radius of tank 1 is going to be equal to 4.0. Radius of tank 2 is going to be equal to 2.0. The next is going to be the area of the pipe. So the area from pipe the area of the pipe from tank 1 to tank 2 is going to be equal to 0.2, and both pipes are going to be the same area. So A2, the pipe exiting tank 2, is also going to be 0.2. Next, we want our initial height. So height 1 is going to be equal to 5.0, and then height of the tank 2 is of the water level in tank 2 is going to be equal to 3.0. So now that we have that, I'm going to also create a variable for the square root of 2 times gravity, so I don't have to be typing that out through the whole time. I'm going to label this square root of 2g, and that's just going to be equal to JNP of the square root of 2 times 9.81, the acceleration due to gravity. And we're also going to be working on the time, based on the time throughout this whole problem, and so we're going to needing to establish a time end, because we're going from 0 to some time end. And what I'm going to do is make t end equal to 2000. I'll explain more about that later on as we continue coding, more for our dHdt variable, which we'll be plugging into the initial value problem solver. But we'll get there in just a moment. For now, we should stick to coding out the flow rates. So Q12 initial, this is what we did on the OneNote, this is what we solved for, and this is going to be equal to the area of the pipe from tank 1 to 2 times the velocity, which we found the velocity to be the square root of 2g, so this is where you use the square root of 2g, times the square root of the absolute value of height 1 initial minus height 2 initial. We want to use absolute value here because we can't get a negative number under our square root. But to make up for that, we can go ahead and do JNP.sign, and what this does is if it is a negative number, it'll just multiply the whole thing by -1, but if it is a positive number, it will just keep it multiplied by 1. It sets this variable to 1 or -1 based on a positive or negative number. That is our Q1 to 2 initial. Now we have to do Q2 initial, which is going to be equal to the area of the pipe 2 times square root 2g times the square root of height to initial. Perfect. So we are at steady state to start, so we can go ahead and make Q1 initial, which is the flow coming in from tank 1. That's going to be equal to Q12 initial. And then for Q2 initial, which is the flow coming into tank 2 from the top, is going to be equal to Q2 initial minus Q12 initial, because the in has to be equal to the outflow for a steady state. So we make sure we run that, and H2 initial is not defined, so we have to go back and make sure that is the initial. And it should run, and I do like to be able to print the statement here just to make sure our values look appropriate. And so we put this in the bracket. We want to say equal, and then squirrely bracket, Q12. This is where you put the variable. There we go. And then you click Shift Enter, and it should print out these values for you. So that does look correct. So now we have to think about what we're going to be doing moving forward and what we solved for in the OneNote. So one thing that we did solve for in the OneNote is the cross-sectional area, and so we're going to be needing a function to do that because it is based on radius and height. So that's the first thing I'm going to do, is going to be defining a variable of AC with the parameters of, we'll do H, which is the height of the tank, and then R for the radius of the tank. I like to capitalize R. I like to keep these two separate so I know which one it's referring to whenever it comes up. And what this is going to return, like we saw for before, it's going to return R to square root, or to the power of 2, R squared, minus, and this is in parentheses, it's going to be R minus H squared, and of course it's going to be this value times pi, and for pi we just do J and P dot pi. And I had a typo there at the end, and that is what we get. So that is our function for our cross-sectional area of the tanks at any height that we choose and any radius. Of course, our radius in this is going to be constant. So next, we want this to be a little bit more realistic. So we do want to be able to turn or have a switch factor in on the tanks for the flow rates. We want to be able to change the values at a certain time, and we want to be able to set that up. So I'm going to define a switch function. Parameters for this are going to be time, the time at which we want to switch it, V1 or V initial, that's the flow rate initial, and then V2 flow rate after what we want to change it to. And then we also want to have a scale factor in there because we're going to be using a sigmoid function. So we want to, and this is going to return the sigmoid function as I just said, and we have to use JAX for this. That's why we imported JAX up here. And we are going to do NN. NN stands for neural network, and it's .sigmoid. And so we have the sigmoid function for T, and we want to move it to the left. We want to have just, it's basically a graph, so we want to have a shift to the left of T switch, which is the time we want to switch it at. And this is going to be all in parentheses because this is going to be over our scale, whatever we decide the scale to be. It's going to compress it, and then we're going to multiply this by V1 or V2 minus V1, and then we're going to shift it up Shift Enter, make sure that all makes sense and the code can read it. Perfect. So now that we have that, we do want to create functions for when we want to change, when we want to make this switch for our flow rates. So for flow rate in 1, we're going to do flow rate in of t, because it is going to be a function of time. I forgot to define here out in front. Define that. And this is just going to return our sigmoid function, which we just created, switch. And we're going to put all the parameters. T is going to be t, because that is the parameter for this function, this new function, which was going to be varying all the time. T switch, we want this to be changing at 100. Initial value is going to be q1 ini. And then what we want to change it to, we're going to make it 80% of what it was. So multiplying it by 0.8 does that for us. Q1 ini. And then the scale we will be using is 0.01. The scale is basically how gradually or how how quick or how long you want the curve to be. And I'll explain that when we start making our plots. So I'm going to go ahead and copy this, because it's going to be the exact same thing for our Q2 in, except for we're going to be changing the values. This is going to be at 200 seconds is when we want it to switch. 0.8 now becomes 2.5. It's going to be 250% of what it used to. Make sure we change these variables inside as well. And there it is. So now that we have all this set up, we can go ahead and make our dh over dt function, which is what we will be using in the initial value problem to be able to solve it. And this is also what we did on the OneNote before we started the coding section. We have to start plugging in some real values for this now. With our initial value problem, then we'll be able to plot it. So we're going to have two variables, two parameters, obviously h, because it's the change in height, and then t, over the change in time. And this height is actually going to be an array, and in Python the arrays always start at an index of 0. So we're going to be setting h1, this is going to be a new variable, h1 is going to be set at the index of 0, and then h2 is going to be the index of 1, which index of 0 is the first value, and then 1 is the second value. So that all makes sense. And now what we want to do is we want to go ahead and go up here and copy this, because it's going to be the exact same. Our equations have not changed. But we don't want these initials in here anymore. This is going to be constantly changing values. H2, initial, take out all of the initials. Alright, and now once we have that, we want to go ahead and make our return statement. And what this is going to be returning, it's going to be returning the flow rate, or the change in height of tank 1, and then the change of height in tank 2. So for that, we need we solve for the dh dt equation for both. So the first one is going to be, I like putting this in parentheses, it's going to make q1 of what we just did, in of t, that switch function that we created with used q1 in. It's going to be that minus the out, so in minus out, which is going to be q12. And this is going to be divided by the cross-sectional area like we solved for before. So we use our function for cross-sectional area, and we want to use height 1, because this is tank 1, and then r1, our value of radius 1. And once we have that, now we want to do it for the second tank. So the in is going to be q2 in function of t plus q12 minus q2. Both ins minus the out will give us our change in height. And this also has to be over the cross-sectional area of that second tank, so we use the function AC again. height this time is going to be 2, and then R is going to be R2. Shift after that, it looks good so far. So now what we're going to go ahead and do is solve for our initial value problem. And to do this, we need to set a variable to what we want it to be, and I like using res. So res is going to be equal to solve underscore IVP and solve initial value problem. And then it tells us exactly what we need. We need our function, dh dt. Time span, we want our time span from 0 to tn. That's why I created the tn variable up here. We need our initials, our initial heights, so h1in, or h1i, I apologize, and then h2i. Method, we will be using the Radal method to be solving this. And then we want our dense output to be equal to true. Make sure that t is capitalized, because if it is lowercase, then it will not work. And once we have that, we can go ahead and move on to the next part. So we want to be able to set a list of values to tplot. In order to do this, we do linspace. You need J and P dot linspace. Linspace, if I can spell, perfect. And the starting number is going to be 0. Ending number is going to be tend. And how many values we want in there. I like to just do all of the values, so that in this case it's going to be 2001. And then we need to set a variable to the solution of res, because res is going to be a whole bunch of different things. So we just want to cut out the solution, and I like doing sol for solution there, and then we just set that to res.sol, and over that we need to do tplot. So once we have that, we want to go ahead and click run to make sure everything works correctly. And it is going to take a while because we did select a lot of values. 0 to 2000 is a lot, and we just have to be patient and wait. It'll come to us eventually. Boom, and now it didn't give us any poor feedback, so that means that's really good. So now we want to be able to plot our data that we got. So we need to create a variable to be able to set the graphs to, and this is going to be fig, make subplots, and we can select how many rows and columns we want. So we want the rows to equal to 1, and we want columns to equal to 2. And this will allow us to graph height, the change in height on one side, and then the flow rate of Q1 in and Q2 in on the other side. So once we have that, we can do fig.add_trace, and that will add a line on our graph, or our function on the graph, to whichever graph we choose. In here, we need to use our graph objects, and we'll do scatter command. And then this allows us to pick our x and y variables. So x is going to be equal to tplot. Y is going to be equal to the solution of 0 index, because this is for height 1. And we can also name it inside this. So we want name equal to height 1. And then outside the parentheses, we can decide what column and what row we want it in. For this, I'm just going to do row equals 1 and column equals 1 as well. And then shift enter that to see if it makes our plot, and there it is. This is exactly what it should look like. And for this, right at 100 is when it starts to drop. This is a sigmoid function. If we were to select a higher scale, it would drop off way more gradually than this sharp edge. Here, I'll show you. Let's do I'll show you after we finish making the other plots, just to give a quick insight on that. And so what I'm going to do is I'm going to go ahead and copy this so I don't have to keep typing all that information. We're going to do this for height 2. So what we want to do is change sol 1, sol 2, and it should just go ahead and add another graph onto that, and look at that, it does. So here, initial 3 is what we made it to, and then at 200 seconds right here, boom. This is the sigmoid function that we use. And the reason that this is changing right here is because our Q1 initial is changing. If our Q1 initial is changing, then our Q12 is changing. So it all is sort of a bounce effect, domino effect, I should say. So now we want to go ahead and copy, or we want to go ahead and make plots for our Q1 and Q2. So instead of doing this right here, we're going to do our function Q1 in of t. See if that goes ahead and gets us that. Oh, t is not defined, of course. T plot. Oh, and then we want this onto column 2, so it creates a graph on the other side. There we go, and we don't want this. We want this to be Q12, Q in. And then we'll go ahead and copy this, make this 2, change this to 2. And there you have it. There is our graphs, all nice and neat. And this is perfect. It looks very good. So thank you guys so much for watching. I told you guys I would show you what happened if you did change the scale. It does take a little bit longer, but say we change it to 10, which is quite the increase. Make sure we shift enter all of these to make it update. And now it has to wait for res to finish doing its initial value problem solver. But thank you guys so much for watching. I hope you guys have an excellent day. Once this pops up, I'll go ahead and show you. It takes a while. It does take a while. And see how it does, it's not as sharp on these edges right here. They're not as sharp. So that's what that does, and it also is not as sharp on this side over here. So thank you guys so much for watching.